Thank you for the warm introduction. To begin, I'm going to give some thanks. So I'm going to start with my undergraduate research mentor, Margaret Burnett. She was the one who really invited me into research, who introduced me to HCI and software engineering. She taught me how to think, how to read, how to develop scientific arguments, and she helped me navigate to graduate school, connecting with other mentors. I simply wouldn't be here if she hadn't mentored me for the past 20 years. So thank you, Peggy. I also want to thank my PhD advisor and co-author on this work, Brad Myers. He taught me how to choose great projects, how to convey the essence of their insights, and he really seeded me with this early idea of asking systems to explain themselves, which eventually led to the work on the Whyline. His relentless constructive critique, but availability really helped me learn incredibly fast during graduate school, and I'm so grateful for all of his feedback. I also want to thank you, this community of software engineering. You taught me technical rigor. You really tested the limits of my humanism coming from a field of human-computer interaction. And you provided me with really 3 decades of really powerful ideas about dependencies and analysis and architecture, program comprehension, encapsulation. These are things that I didn't get in my training in HCI, but were really central to a lot of my research contributions over the past 20 years. And finally, I want to thank all of academia. It might seem a bit grandiose, but I've been really fortunate to have dozens of really outstanding teachers and mentors in my life, and all across all of the different subjects: math, physics, sociology, psychology, neuroscience, business, English, philosophy, design, art, learning, even chemical engineering, of all things. And my ideas are really just compositions of all of the ideas that I've learned from my teachers in the past. So I'm really grateful to now be one of those teachers and see my role in a larger, broader community of innovators and inventors and scholars. So it's in that spirit that in this talk, I want to talk a lot less about me and my work and a lot more about the ideas and where they came from, and try to convince you that trying to discover ideas through a community process and not just through a personal process is really a much more impactful way of trying to change what we know. And I'll use the Whyline to try to illustrate some of these ideas. So let me give a brief primer on the project itself. So here's the paper that was recognized. This was 10 years ago, published at ICSE in Leipzig, Germany, about 900 kilometers south of here. There's actually 4 papers that spanned about 7 years of research during my PhD and the first couple of years of faculty life at the University of Washington. And I'll try to capture the essence of the idea in just one slide. Here's the key theoretical insight. What I observed was that debugging is slow because developers iteratively test really brittle hypotheses about what caused the failure by manually collecting runtime. And this causes them to bounce around to different possible explanations, different parts of runtime history in order to isolate the cause. And it's this bouncing around that's inefficient. So the observation was that debugging would be faster if developers worked backwards from well-understood failures to cause, relying on the dynamic dependencies that we could precisely gather with a tool. This is essentially a root cause analysis strategy. And so this is in essence advocating for root cause analysis as an approach to debugging rather than the scientific method. And it's really more a theory about human problem solving than it is about tools. But to demonstrate evidence for this theory, I embodied it in a tool so that I could show that this strategy was better. Here's how the tool worked. It recorded an execution trace and reproduced an interactive timeline of all of the output of an application. And then it allowed developers to select questions about properties of output that they knew to be wrong so that they could start from something they were certain about. And then the tool gave them an answer in the form of a precise backwards dynamic slice on that output property that they'd selected. But in a key way, it presented that slice interactively, allowing developers to navigate causes one dependency at a time, using all of their knowledge of architecture and requirements of the system they were interrogating to identify the defects, rather than presenting the whole slice at once. And this worked really well with novices. They debugged 8 times faster with the Whyline than without it. Novices with the Whyline debugged the same defects twice as fast as experts without the Whyline. And experts with the Whyline were 3 times more successful at localizing faults in a fixed amount of time and twice as fast than experts without it. So these are sort of large effect sizes on the impact on debugging, ultimately boiling down not just to the benefits of this tool, but this idea that root cause analysis is a more effective strategy than doing the scientific method of hypothesis testing. This had a lot of impact. I'll try to gloss over this quickly. Lots of papers, lots of citations. It impacted lots of different fields of computer science, software engineering, HCI, computer science education, databases, programming languages. And so I won't go into any of that in depth. And it also had some industry impact. So it caused Adobe to start looking into debugging tools like this for Flash and other design tools. Microsoft built upon many of these ideas in some of their more recent debugging tools that they've released. Apple, and one of my students, has been working on some of these tools for the Safari web inspector. And Code.org, which is advocating for K-12 computer science education, has been building this into some of their environments as well. So this idea is slowly making it out there into products. It turns out to be pretty difficult to build. Now, these ideas and this evidence and this impact are really great, but how much credit do I really deserve? I really built on the shoulders of giants, and so I want to talk about some of this inherited wisdom that allowed me to get to these innovations and really only give me sort of a fraction of that credit. So here's practice number one. Reading accelerates innovation. Linus Pauling, a Nobel laureate and one of the alums of my alma mater, Oregon State University, said the way to get good ideas is to get a lot of ideas and throw the bad ones away. And I saw this quote every day as a student at Oregon State, where Linus Pauling was a student. And one of the things I took away from seeing this quote all the time was to never forget that there really are hundreds of thousands of papers in all of the archive of human knowledge that are full of powerful ideas and that we should really use them. So when I was starting this project for the Whyline, I really spent 3 months reading more than 900 papers about debugging and diagnostics and human error and root cause analysis, well beyond the boundaries of computer science, to really get the best understanding of what it was that humans were doing when they were trying to diagnose failures. And that was really powerful, and that really accelerated a lot of my innovation. One of the papers that was from sort of computer science that influenced my work was this paper that Mark Weiser cited in his program slicing paper by Gould on exploratory study of computer programming. This was a psychologist. It showed that debugging required analyzing data flow. The developers satisfied their data flow analysis. They didn't do it completely and systematically, and that they analyzed a lot more irrelevant statements than relevant statements. And so this was that observation I was building upon, that this scientific method was not particularly effective as a strategy. And this was the foundation for my research, but it was from a paper written by a psychologist that was 26 years old when I started the work. And the really valuable insight here wasn't program slicing, but this underlying theory about how slicing might help by focusing developers on what to analyze. So that was a key practice, and it was that reading that really shaped my ideas. The second practice here is that observation that develops insight about a phenomenon is really critical. So Alexis Carrel, another Nobel laureate, said, "A few observations and much reasoning lead to error. Many observations and a little reasoning lead to truth." And so as an HCI researcher, I took this to mean that if I didn't deeply understand the experience of debugging that developers have of all kinds of expertise, I wouldn't really have the insight to simplify it, no matter how much I reasoned about it. And that's a really interesting observation for this field, which does a lot of reasoning and a lot less observation. And so one of the things that I did before working on this project was I spent 3 months after reading to observe people debugging, hundreds of novices and experts, and really interrogating my own debugging. And it led to this really rich intuition about debugging that helped me predict the utility of the design choices I was making while I was envisioning the Whyline. And I still use this intuition today to judge the utility of my research ideas, my students' ideas, the ideas that this community publishes, and when I'm peer reviewing them. So we really can't discount this intuition in shaping the more objective work that we do in science and discovery. Now, the third practice, again, not my own, is about explaining why, not just how, and really getting into theory. So Da Vinci said, "He who loves practice without theory is like the sailor who boards ship without a rudder and a compass and never knows where he may cast." And this was a quote that really drove a lot of my thinking about how to approach the research that I was doing. So I took this to mean that the true value of inventions is not in explaining how they work, but why they work. These explanations are really the generalizable knowledge that stand the test of time. They're the thing that guide us when we're taking a tool and trying to figure out how to manifest it in some other context. It's that underlying explanation of a tool's benefit and its mechanisms that are the key understanding. And so when I look at the Whyline, the key thing that made it work was that I synthesized this intuition about debugging into a theory of how people debug and how tools mediate their strategies. And it was really this theory and not the tool itself that was the core of the Whyline's innovation. The tool was just an embodiment of that theory, and it helped me test and refine the theory, but the underlying idea that you're going to take away from it is that theory and not so much the implementation that I created. It's not to say that engineering had no value, but it wouldn't have had value without that theory, and we wouldn't know when to use that engineering know-how. So none of these practices and none of these ideas were my own. I assembled them together, and that's what allowed me to make these discoveries. But following these practices and composing them as I did, I do think that there were some new discoveries, and they've slowly become clear to me 10 years after publishing the work and doing a lot of collaborations on things building upon these ideas. So I want to share a couple of those that I think are relevant to software engineering research. So the first is that I've come to believe that automation is just universally insufficient to solve problems. When you look at what Mark Weiser said in the program slicing paper, he said, in practice, slicing is fairly fast and can often eliminate large numbers of unnecessary statements from slices of programs. This is not at all a claim about the usefulness of a slice to a developer, right? And that was a sort of untested claim. And astoundingly, after 4,500 papers that have cited the program slicing paper, incrementally sort of improving the optimization and accuracy and so on of slicing techniques, only 3 of these papers actually investigated whether or not slices are useful to developers as an idea. And all 3 of these studies found that slices are too large, hard to navigate, and incomprehensible at scale. That's a sort of damning consequence of a lot of investigation, to know that most of those papers that built upon this idea of slicing just didn't really work, that they weren't really actually useful in practice. So the key mistake that we made was assuming that useful slices are trivial for developers to express. It turns out that developers don't know what slice to express, and the slice of a slice that determines its comprehensibility. And that's actually not true either. And I showed in the Whyline that both of these are not true, and that making slicing useful really required a new paradigm for expressing a slice, a new paradigm for navigating a slice, and really re-architecting of what program slicing is to align it with these interactive paradigms. Now, since the Whyline, others have shown that automation is also insufficient for other technologies to be useful. So in refactoring, in static analysis, in machine learning, most of what we found here is that when you put a human in the loop with these systems, most of this automation sort of breaks down, and it requires a careful integration with the developer's understanding and abilities to make these tools valuable. This is probably also true for formal verification, for synthesis, for testing tools, for automatic bug patching. And so we should be looking at some of these interactive questions. And this sort of leads to this final observation that I think the Whyline revealed, which is that we like to believe that with enough data and the right algorithms, our tools can really outperform humans. And the Whyline showed that this really overlooks the power of developers' knowledge and intuition. In the evaluations of the Whyline, participants interacted with slices that were 50,000 lines of code if they had been presented in entirety. But by leveraging their knowledge and their expertise and their intuition, the developers in the study only ever looked at a few dozen lines of code, and they still found the defects, right? Something very powerful is happening there that program slicing tools just simply weren't able to reduce upon. And so there's a couple of consequences of that, of ignoring what developers know. And that's first, that our innovations often aren't useful at all because they often don't have as much knowledge as a developer, and we don't really think about what developers know. And then second, we miss opportunities to really combine that human knowledge with machine insights to achieve an even greater power. So really what we need to be doing here is inventing for the entire system of not just tools alone, but tools and developers, tools and teams, tools and organizations. And then we'll actually get real practical utility out of the innovations that we create. So just to summarize this wisdom I've received and some of the things I think that this work has triggered, read everything in and outside of CS that's relevant to your work. Use it to build upon the best ideas that we have in academia, not just the ideas that you can find in the last few ICSE proceedings. Second, reasoning is insufficient. Try to develop a rich observational instinct for software engineering practice or whatever part of software engineering you're trying to improve. And use that instinct to make decisions and to develop theories and try to understand how it is that you can improve software engineering practice. Third, don't just invent tools and describe them. Explain why they work, when they work, for whom they work. This is the kind of knowledge that will stand the test of time, and this is the kind of knowledge that will impact practice and product. Fourth, don't assume automation is ever enough. Developers know more than you think. And fifth, find ways of leveraging that knowledge that developers have to create augmentations that really make developers more powerful than they could ever be with pure automation alone. Thanks for your time and attention and this recognition, and I'd be happy to take questions.